Good day everyone, and this is a continuation of our lesson in reaction stoichiometry. So these are just special topics involving stoichiometry of solutions and gases. So we will just be solving some additional examples for stoichiometry of solutions and gases. So let's begin. Okay, let's start with solution stoichiometry. Solution stoichiometry is quite commonly encountered, no, especially in your laboratory. So for this, we have to recall the concept of molarity. Molarity is just one of the few ways on how we can express the concentration of a solute in a solution. Molarity is defined as the number of moles of your solute divided by the volume of the solution in liters. Okay? Normally in these types of problems, your solvent is almost always going to be water for it to become an aqueous system. Let's apply this concept of molarity to this example. A 2.5 gram piece of magnesium is dropped into a beaker containing 50 ml of 1.20 molar hydrochloric acid or HCl. And this is our reaction. Magnesium plus HCl yields MgCl2 plus hydrogen. We are to determine how much magnesium chloride in grams is obtained from the reaction. So let's first write the given. Our reaction is magnesium plus HCl yields magnesium chloride and hydrogen gas. Let's take a look at the numerical given. So we have 2.5 grams of magnesium. And for HCl, you have two parameters given here, the volume of the solution and the molarity of the solution. Both of these numbers are very important because you want to determine the number of moles of your solute. In this case, that is HCl. So we write that we have 50 ml of 1.20 molar HCl. It is from these two numbers that we determine the number of moles of HCl. Okay? And the problem is asking us for the mass of magnesium chloride that was produced from this reaction. Okay, let's start with the HCl. Again, the definition of molarity is moles of solute, in this case your solute is HCl, divided by the volume of the solution in liters. We are given the molarity. You are also given the volume of the solution. We just have to convert it to liters, and then we can solve for the number of moles of HCl. So by cross multiplication, we get that the number of moles of HCl is equal to the molarity multiplied by the volume of the solution. So let's compute. The molarity is 1.2 molar, and the volume of the solution is 50 ml. Although we have to convert this to liters, you simply divide by 1000 ml is to 1 liter. Okay, so the number of moles of HCl is 1.2 times 50 divided by 1000. That is 0.06 moles HCl. The next step is to determine which among magnesium and HCl is your limiting reactant. Again, it's important that you do not forget your concept of the limiting reactant because even though it's not being stated explicitly in the problem, you still have to consider solving for the limiting reactant. Okay? So let me first just clear some of this. We now know that the amount of HCl is 0.06 moles. Now let's convert the amount of magnesium to moles, and then let's see how much magnesium chloride can we produce. So we start with 2.5 grams of magnesium. Let's take a look at the molecular weight of magnesium. Magnesium is here, that's 24.305 grams per mole. Okay, and then let's take a look at the balanced equation. By the way, we have forgotten to balance the equation. So balancing our equation, you take a look at magnesium, so it's already balanced. You have one magnesium on both sides. Hydrogen, you have two hydrogen on the product and one on the reactant. So we have to multiply HCl by 2, and consequently, that also balances chlorine. 2 chlorine on the reactant, 2 chlorine on the product, we're good to go. Okay? Based on the balanced equation, if we're solving for the amount of magnesium chloride, for every 1 mole of magnesium, there is 1 mole of magnesium chloride. And since the problem is already asking us for the amount of magnesium chloride in grams, let's continue our conversion to grams. We simply want to convert the number of moles of magnesium chloride to grams of magnesium chloride. And for that, we need to get the molecular weight of magnesium chloride. So let's go back to our periodic table and let's take a look at magnesium and chlorine. Magnesium has a molecular weight of 24.305 and chlorine has a molecular weight of 35.45. So that would be 24.305 for magnesium plus 35.45 times 2 for chlorine. The molecular weight is 95.205 grams per mole. We need to multiply the number of moles by the molecular weight. So this becomes 95.205 grams of magnesium chloride for every 1 mole of magnesium chloride. You know that we are on the right track because when you cancel the units, grams of magnesium cancels, mole of magnesium cancels, and mole of magnesium chloride cancels, your remaining unit is grams of magnesium chloride. Okay, let's solve for that. That would be 2.5 divided by 24.305 times 95.205. We have 9.79 grams of magnesium chloride. However, this is not yet our final answer. Okay, we still have to take a look at how much magnesium chloride will be produced coming from HCl. So if we start from HCl, you have 0.06 moles of HCl. It is already in moles, so we can now go to the balanced equation. The balanced equation states that there are 2 moles of HCl for every 1 mole of magnesium chloride. And then we can convert the moles of magnesium chloride to mass by using the same factor that we used earlier, the molecular weight. We multiply this by 95.205 grams of magnesium chloride per mole of magnesium chloride. Cancel the units, moles. You're left with grams of magnesium chloride. So that is 0.06 divided by 2 times 95.205. And our answer is 2.86 grams of magnesium chloride. Based on our 2 answers, what do we choose? We choose the lower one, and we say that HCl is our limiting reactant and magnesium is our excess reactant. So we say that the 9.79 grams of magnesium chloride is the wrong answer because it came from the excess reactant. Going back to the problem, we are just tasked to determine how much magnesium chloride is obtained from the reaction. Our answer is 2.86 grams. Okay, that is how we apply stoichiometry in solutions. You just have to remember the concept of molarity. Let's have another example. Calcium carbonate is known to be insoluble in water. If you mix 50 ml of a 0.125 molar calcium chloride solution with 50 ml of a 0.112 molar sodium carbonate solution, what mass of calcium carbonate can be recovered? This is another one of those examples wherein you're not given the chemical equation. So we have to decipher the chemical equation from the given. Based on the problem, we are mixing 2 solutions, one sodium carbonate and the other is calcium chloride. So let's see what happens when we mix those 2. Sodium carbonate plus calcium chloride. This looks like a double displacement reaction wherein the sodium will be partnered with chlorine and then the calcium will be partnered with the carbonate because the problem asks us how much calcium carbonate can be recovered. Okay? So our products in this case would be sodium chloride plus calcium carbonate based on the double displacement reaction. Now to balance the equation, we simply multiply sodium chloride by 2. To check, sodium is balanced, that's 2:2. Chlorine is also balanced, 2 is to 2. Carbon, 1 is to 1. And oxygen, that's 3 in the reactant and 3 in the product. So this is already a balanced equation. Now let's take a look at the other given. You're given the volume and the concentration of both calcium chloride and sodium carbonate. So for calcium chloride, that is 50 ml of a 0.125 molar solution, while for sodium carbonate, that's still 50 ml, but the concentration is now 0.112 molar. And we are solving for the mass of calcium carbonate. Okay, so our given is now complete. Now, you just have to recall again the concept of molarity. Again, molarity is equal to the moles of the solute divided by the volume of the solution in liters. We are already given the volume. We're also given the concentration in molar for both of our reactants. So we simply have to convert them to moles and then determine which among them is the limiting reactant. Then we can solve for the amount of calcium carbonate that can be formed. Okay? So based on our formula here, if you want to determine the moles of the solute, you simply have to get the product of the concentration in molarity and the volume of the solution in liters. So let's do that. For sodium carbonate, we simply multiply 50 ml but divide that with 1000 to make it liters. Remember that the denominator of molarity is always liters. So if you're given a solution volume in milliliters, do not forget to convert it to liters, okay? So that is 50 divided by 1000 to convert it to liters multiplied by the molarity of sodium carbonate solution, 0.112. The number of moles of sodium carbonate is 5.6 times 10 raised to negative 3 moles. Next, we do the same for calcium chloride, that is 50 divided by 1000 to convert it to liters, multiplied by the concentration 0.125. The answer is 6.25 times 10 raised to negative 3 moles of calcium chloride. Now, let's determine which among the two is the limiting reactant, and let's determine the amount of calcium carbonate that can be formed. Let's start with sodium carbonate. That's 5.6 times 10 raised to negative 3 moles of sodium carbonate. This is already in moles, so we can proceed with the balanced equation. For every 1 mole of sodium carbonate, we have 1 mole of calcium carbonate as well. And we want to convert the moles of calcium carbonate to mass because we are asked for the mass of calcium carbonate. So let's solve for its molecular weight. The molecular weight of calcium is 40.078. So that is 40.078 for calcium, plus for carbon, that is 12.011, and then 3 oxygen at 15.999 each. The molecular weight of calcium carbonate is 100.086 grams of calcium carbonate for every mole of calcium carbonate. Cancel the units. What do we have? That is 5.6 times 10 raised to negative 3 times 100.086. We get 0.56 grams of calcium carbonate if we started with sodium carbonate. But at this point, we have nothing to compare it yet, so we need to solve the one from calcium chloride. We start with 6.25 times 10 raised to negative 3 moles of calcium chloride. And then based on the balanced equation, for every 1 mole of calcium chloride, there's also 1 mole of calcium carbonate. And then we use again the molecular weight of calcium carbonate, 100.086 grams of calcium carbonate per mole. We can determine the mass of calcium carbonate produced. That is 6.25 times 10 to the negative 3 times 100.086. We have 0.626. So which among the two values do we choose? We choose the lesser value. We say that we can generate 0.56 grams of calcium carbonate, and that sodium carbonate is our limiting reactant. Okay? We cannot generate 0.626 grams of calcium carbonate because that would be in violation of the limiting reactant. Okay? So it's basically the same approach in stoichiometry, but we are now adding the definition of the molarity. Okay? So always keep this in mind. Let's continue. For the final part of this additional lecture, we have stoichiometry involving gases. The stoichiometry aspect would still be the same. However, the main difference here is that we are dealing with gases, so we have to use the ideal gas law. Because the number of moles is very hard to measure in gases, we often rely on other parameters such as temperature, pressure, and volume to determine the amount of gases present. Okay? If you will recall, the ideal gas law is characterized by this equation. That's PV equals nRT, wherein P is pressure, V is volume, N is the number of moles of the gas, R is the real gas constant, that's 0.08206 liter atmosphere per mole Kelvin, and T is the temperature. So you only need to know the pressure, the volume, and the temperature to know the number of moles of the gas. And it is this number of moles of the gas that we can use in stoichiometry. Let's try to solve this example. We basically have the same problem. A 2.50 gram piece of magnesium is dropped into a beaker containing 50 ml of 1.20 molar of HCl. It's the same reaction and the same given. However, this time, we want to determine how many liters of hydrogen at 25 degrees Celsius and 1 atmosphere is obtained from the reaction. So we are now interested in the amount of hydrogen. Here's our given. So this given is the same as that of our previous example involving the same reaction. From that problem, we have determined that the number of moles of HCl is 0.06 moles and that HCl is our limiting reactant. But in this case, we want to determine what volume of hydrogen is being produced given that the temperature is 25 degrees Celsius and the pressure is 1 atmosphere. Let's try to solve this. Since we know what the limiting reactant is, we can already proceed to the determination of the number of moles of our products, which in this case is hydrogen. So we start with 0.06 moles of our limiting reactant HCl, and we want to determine how many moles of hydrogen can we produce. Based from the balanced equation, for every 2 moles of HCl, we produce 1 mole of hydrogen gas. So our answer is 0.03 moles of hydrogen gas. And with the number of moles of hydrogen gas given the temperature and pressure, we can easily solve for the volume of the gas using the ideal gas law. The ideal gas law, PV equals nRT. We want to determine the volume. So we divide both sides by the pressure. We get nRT over P. And we can substitute everything and solve for the volume. Solving for the volume, the number of moles as we have determined is 0.03 moles of hydrogen gas multiplied by R. Remember that R is a constant. That's 0.08206 liter atmosphere per mole per Kelvin. And then temperature is always in Kelvin. So you need to convert 25 degrees Celsius to Kelvin. You simply add 273.15 to make it Kelvin, divided by the pressure of 1 atmosphere. Now, if you want to double check if you are correct in the derivation of the formula coming from the ideal gas law, you can try canceling the units. Moles would cancel, Kelvin would cancel, and atmosphere will also cancel. That leaves you with only one unit, and that is liters. So we know that we are correct. Okay? Solving, we can solve for the volume of the HCl. That would be 0.03 times 0.08206 times 25 plus 273.15 divided by 1. That is 0.734 liters. Okay, that means that we can produce 0.734 liters of hydrogen coming from this reaction at 25 degrees Celsius and 1 atmosphere. Okay, the approach is still the same. The only different thing in this case is that this involves gases and we have used the ideal gas law for the computation of volume. Otherwise, it's the same process. Let's solve for the last example. Calburo, or calcium carbide, is a compound used by fruit growers to artificially ripen fruits such as mangoes and bananas. When reacted with water, it produces acetylene and calcium hydroxide according to this reaction. That's calcium carbide plus water yields acetylene plus calcium hydroxide. If 55 grams of calburo or calcium carbide is reacted with a large excess of water, determine the volume of acetylene that can be recovered at 30 degrees Celsius and atmospheric pressure. Okay, so let's list the given. You are given here the complete chemical reaction, so that's good. And it was also stated that water is provided in excess. That means that water is your excess reactant and calburo or calcium carbide is your limiting reactant. So we are given 55 grams of calburo. We want to determine the volume of acetylene at 30 degrees Celsius and atmospheric pressure. And here is our given. Let's first try to balance our equation. Calcium is already balanced. Carbon, 2 is to 2, that's already balanced. Hydrogen, we have 2 in the reactant and you have 4 in the product. So you have to multiply water by 2 to make it balanced. And oxygen is 2 in the reactant and 2 also in the product. Okay, so what is our plan here? Our general plan is to take the mass of the calcium carbide, convert it to moles of calcium carbide, and then use the balance equation to turn it to the number of moles of acetylene, and then later use the ideal gas law to convert from moles of acetylene gas to the liters of acetylene. Okay, let's begin. We have 55 grams of calcium carbide. We need the molecular weight of calcium carbide. Calcium is 40.078 plus for carbon that is 12.011 times 2. The molecular weight is 64.1. Grams of calcium carbide is to moles of calcium carbide. Next, we take a look at the balance equation and look at the coefficients. For every 1 mole of calcium carbide, there is 1 mole of acetylene or C2H2. Okay, now we can solve for the number of moles of calcium carbide. That is 55 divided by 64.1. That's 0.858 moles C2H2. Now, as with our previous problem, at this point, we simply need the ideal gas law. That's PV equals nRT. Solving for volume, that becomes nRT over P. And substitute everything, we can find the volume of acetylene. Okay, so the volume is equal to number of moles 0.858 and then R 0.08206 liter atmosphere per mole Kelvin multiplied by the temperature 30 degrees Celsius converting to Kelvin plus 273.15 divided by the pressure 1 atmosphere. Solving, this 0.858 times 0.08206 times 30 plus 273.15. We get 21.3 liters of acetylene. Okay, so you see that the solution is just repetitive. You just have to master how to perform stoichiometry and then apply additional equations such as the ideal gas equations for stoichiometry involving gases and the definition of molarity for solution stoichiometry. Please watch out for another video release detailing the solutions for more examples so that you can practice. Okay, That's the end of this video. I hope you have learned something. If you have questions, you can always send me a message. Keep practicing, and as always, keep safe.